So we're going to talk about enzyme activity in this video. And when we think of enzyme activity, we're talking about, the things that affect the activity or how fast an enzyme goes. And so this is C, enzyme activity. And I am going to start with the idea of turnover rate. So when you think of a turnover rate, it's basically um, how much product is produced by an enzyme over a given amount of time. So the amount of product produced by an enzyme over a given time. And that can be, some people talk about seconds, it could be minutes, it could be hours. Usually it's pretty fast though, seconds or minutes. This really has to do with, if you think of an enzyme and a substrate, sometimes enzymes and substrates, they can go back and forth, like they have a rate constant of forming and a rate constant of going back to the reactants and substrates separately, but then they have this, they ultimately will form an enzyme and a product. And when I think of turnover rate, if we had more time and we were talking more about enzyme kinetics and how fast they go, turnover rate really deals with how fast this particular reaction is going, dependent on how much enzyme's actually present. So that is what we're talking about. Like, how fast does this happen? Because once the product forms, they don't typically go back the other direction. So I put a double arrow here because there is possibility of binding and not reacting. Over here, once the product dissociates out, it usually doesn't go back the other direction. So the things that I want to talk about that affect this turnover rate or how fast these enzymes are functioning, the first one I want to talk about is temperature. And as you can imagine, temperature affects how fast a particular reaction goes. And so we're going to think about what would take place as you increase. And so I'm going to show you this on a plot here, and I'm going to put increase in temperature here, and we'll go 0 to 100. We're not going to, boil water and have these enzymes continue. And we'll just think of the reaction rate or the turnover rate here. So we can think of turnover rate. So the amount of product that's being produced. You can imagine at low temperatures when something's frozen, it's why you put things in the freezer or refrigerator. There's no enzyme activity, and then it goes up, and then it would come down as you start to get higher temperatures, because we always have this optimal temperature or optimum temp that reactions would take place at. It go at the highest temperature. Our body is probably around 37 Celsius. But as you increase beyond that, what happens is, we just learned that proteins denature. So your enzyme would actually denature as you start to get higher and higher temperatures. But at lower temperatures, they typically don't denature. They just start moving less. And so, but every enzyme has an optimum temperature at which it goes. And we know as you increase, the substrate and everything collides a little bit more, but then at some point you denature your enzyme. And so temperature increases to a point, and then there's an optimum. And your book has a couple diagrams on this too. It shows that there is an optimum temperature, and you get more enzyme substrate collisions as you get faster. And so there is a maximum temperature at which these go. So even when you think of a child or yourself getting a high temperature because you're running a fever, that's dangerous at some point because you start to get into nature enzymes. Okay, so I want you to know temperature affects it. I also want you to know that pH affects it. Okay, and the same type of thing that we could draw, where we put pH here, and it can go from 0 to 0 to 14, our pH scale, and we'd have turnover rate here. And the graph would look similar, right? Where it would peak depending on where it's at in the body. Most things are going to be about pH 7, 7.1, but you could have, right, you could have a protease in your stomach that is the pH is between 1 and 2, and that's the optimum temperature. And so you think of like you have amylase in your mouth at pH 7-ish, and then you swallow it and it must denature in your stomach. And so amylase breaks down starch. And so after a while you start to after you chew and swallow it would denature. And so there is an optimum pH that enzymes function at too. And if they get too high, they denature because you start pulling off that hydrogen, right? The H plus gets lost and you start to, make charges where there weren't charges. And then if you go too low, the same thing happens. You get denaturation again because you put a bunch of H pluses on, you gain them on the protein, and they start to denature and disrupt those R group interactions, and so they denature. So I want you to know that as well. There's an optimum pH for all of these things, and you can see here's a couple enzymes. Most enzymes in your body 7 to 7.5, but you can see that pepsin and trypsin, those are enzymes that break down proteins that some function in your stomach at 2 and some function lower in your intestines at pH 8. Okay. I want you to also be aware that the concentration of the enzyme and substrate have an effect. And if you think back to general chemistry when you learned about rates of reactions, you should have learned like temperature and concentration and catalyst presence and all those things, the types of reactants and products, all those things affect the reaction rate. But if we were to think of the turnover rate again, and we put substrate concentration, now we're in this graph, we're going to assume a constant enzyme concentration. So we're not going to change that. But what's going to happen is you're going to increase, and at some point it's going to level off. And if you think about why that happens, is there's a maximum rate at that if we have a constant enzyme concentration, there's going to be a maximum rate. And we actually have a name for that. It's called the Vmax. And the maximum velocity is what we call it, but it's the turnover rate, really, the maximum amount of enzyme that can function. Because up here, when you start to level off, you have a saturated active site. So you can't get any more substrate into there because it levels off. Okay, so that would be the shape of the curve if you were to do this. The enzyme gets saturated and then it no longer can go any faster. There are some enzymes that move very, very fast though, and they move fast based on the fact that just as things diffuse in and out of the active site, they go in, they don't hold on to them very quickly, the substrates, and so they can go on and come out really fast at the rate of diffusion. I always think that that really is our limitation. If you think of human limitation, we're aqueous solutions, and we can only go as fast as nature allows the diffusion of compounds into our active sites and out of our active sites. So even our comprehension, that's why computers can move so much faster and think so much faster than people, because they're, you can go to the speed of light with light traveling and passing around information. So anyways, the robots may rule the world someday. So that is enzyme, that's substrate concentration. If you had enzyme concentration going, if you just kept increasing the enzyme concentration and you kept increasing the substrate, you should get a linear curve. The rate would, so if you kept adding more enzyme with the substrate, you would get you go faster and faster and faster. But I want you to know mostly at a constant enzyme concentration, that as you add substrate, it's going to level off at some point. Okay. I wrote down a couple rates that I think are fascinating. If you think of turnover numbers, and I keep using turnover rate and rate basically the same thing. So it's a function of how quickly. Catalase is an enzyme that takes hydrogen peroxide and breaks it down into water and oxygen. That's not balanced. That's not my intention. But this can happen with a particular concentration of catalase at about 5 million molecules per minute. Now that is amazingly fast, right? So that's unbelievable. But it's a small substrate, and it doesn't have to be really specific to make that happen. And hydrogen peroxide is pretty reactive. You might have heard of polymerase before, and there's lots of different polymerases in bacteria and eukaryotic cells and human cells. But basically, they add the ATCG to DNA. And there also is RNA polymerase that adds AUCG to RNA, but these only function at about 900 per minute. And you can see it's a lot slower, but it needs to be really specific. If you're trying to replicate your DNA, you want to make sure that that substrate is the exact substrate that went in, and you have what you have. So anyways, I'm going to stop here, and I will pick up on the next video.